I got into a protracted conversation with somebody about when to use this and when to do that. And it was a student in 7th period, and his name rhymes with Zach, and he was very confused about why I spent so much time talking about the difference between these two. Do understand that these are two different things, right? Now, if you don't understand that these are two different things, perhaps it'd be appropriate to have some conversation about that. One of them, I might put a T here to mean tangential. But let me just kind of offer you some insight. Imagine a car driving on this street. A car driving on this street would clearly have to turn the steering wheel multiple ways in order to navigate this street. Would you agree with that? So if the car was traveling with an initial velocity in this direction, it would probably have to turn the steering wheel to the left to be able to negotiate the first curve, and then turn the steering wheel to the right to negotiate the next curve. Agreed? So while we're making that left turn, there would have to be an unbalanced force this way for the car to make it through that turn. And when the car made it to here, well, suddenly it had to turn that steering wheel so that the unbalanced force was this way in order to negotiate the next turn. But while driving, the car is going to have a tangential velocity, a velocity that is tangent to the curve that it's traveling along. So I would say that in both of these cases, you could look down at the speedometer and know what the speed of the car is. You guys understand what I mean by that? You've driven a car, been in one before, so you understand that the speedometer is telling you how fast you are going. It makes sense for this problem that the value that you be given would be the tangential velocity of the car, not the angular velocity of the car. Because although the car is technically traveling in a curved path, and we could describe its motion along that path as being an angular velocity, the car has a speedometer. It would be an unusual way to describe the car's speed by describing it in radians per second as it's driving along the road, right? It's a car. Wouldn't you find that to be weird if somebody told you the car's speed was 25 radians per second? I would find that unusual. Now, contrast that with, say, a merry-go-round. You guys know what a merry-go-round is? Did we have this conversation about merry-go-rounds yesterday? Because I'm scared of merry-go-rounds. Not merry-go, I'm sorry, Ferris wheels. Ferris wheels. Terrifying. So, I still say a Ferris wheel that would, like this one that would be clockwise, would be the most terrifying. If I was up there and it was going that way, that would feel terrifying. But they can go either way. So let's just say that this Ferris wheel is going this way. Let's say that it is. Now, at every portion in this ride, the car itself would have a tangential velocity. And I've picked, obvious locations, but even if the seat was there, there would be a tangential velocity at all those places. Wouldn't you agree? So I could say that at each one of those places and tell you how fast it's going. But to me, the Ferris wheel feels like the kind of object where omega would make more sense. Like I could tell you how many times per second it goes around, or how many seconds it takes for it to go around once. That seems like a more reasonable way of measuring how fast it's spinning, as opposed to how fast a point on the edge is traveling. So to me, this seems like the more reasonable way of describing the velocity, even though in both of these problems, there could be something related to centripetal force. Because in both of them, I see the potential that an object is going to be experiencing some kind of circular motion. It just comes down to which type of object and which circumstance would you be looking at. Might help you decide whether you would want to use this formulation for centripetal acceleration or this formulation for centripetal acceleration. It had never occurred to me that Why you would choose one over the other would cause such consternation, but apparently did, at least for one person. But it was he was so devoted to the argument. It feels like it's worth at least exemplifying a bit in class. So I want to do a Ferris wheel question because I know it's going to bring some interesting things to light. And so I have a Ferris wheel question I want you to consider. And an easy version of the Ferris wheel question, and we're going to work up to a more challenging version. I don't know if we'll get there today or not because I talked about homecoming at the beginning. So let's say this is a big Ferris wheel, but not terribly so. Like something you could go to the state fair and beyond. So we'll say that this is about, I think we'll go 15 meters. So one of the bigger ones at the fair. So pretty big, but not huge. Little kids would be allowed to ride this. Now, if you've ever been on a Ferris wheel, how long does it take to go around a Ferris wheel? Have you watched? Think about it for a moment, because I think we can estimate it pretty good. If you're at the bottom and you're watching somebody, 1,000, 2, 1,000, 3, 1,000, 4, 1,000, 5, 1,000. Does 6 seem like, I think 6 would be pretty quick, but I don't think it'd be terrible. So let's just go a little safer, because slower is safer for a Ferris wheel. Let's say it takes 10 seconds to go all the way around this Ferris wheel. Okay? 10 seconds to go all the way around the Ferris wheel. I know I gave you a time, but you do understand I actually gave you a speed, right? And if you don't understand how, I know many of you do, but I'm not trying to insult you, but I basically said that it's one rotation every 10 seconds. That's basically what I said. Now let's say you're a standard size person of around, I don't know what standard size is. Let's say you're 60 kilograms. That should cover a lot of people in the room. 60 kilograms is about 120 pounds. Some of you are more, some of you are less. Let's say you're a 60 kilogram person and you are riding in the chair. I would like to know, how heavy do you feel at the bottom and at the top of the Ferris wheel? I'm going to say the question again, but then I'll be very specific about what I want. How heavy do you feel at the bottom and at the top of the Ferris wheel? I'm asking for you to find the normal force, because you don't experience weight, you experience normal force. That's how you know that there is weight at all. If you were weightless, meaning you were just falling through the air, you wouldn't know what your weight was. It's the fact that you have the ground there to tell you what your weight is. So I want you to find the normal force experienced on the person at both of these. Now, remember, it's spinning. So this is a centripetal acceleration problem. And even yesterday, that eluded some folks. So I want to talk about what eludes folks here. Let's consider the person at the bottom for just a time being. And I'm going to draw the free body diagram right on top of them. We know that this person has a weight that's equivalent to 600 newtons because they're 60 kilograms. So there's a 600 Newton force straight down. Now that's true both at the top and at the bottom. They don't ever change their weight. What people don't recognize is that they can't travel in the circle if the normal force balances their weight. People think that they have to be balanced to stay on the ride, but that's actually the wrong situation. If the normal force at the bottom was equal to the 600, then they would travel in a straight line. But we don't want them to travel in a straight line. We want them to be pulled upwards, to travel in a curved path, which means that the normal force at the bottom is going to have to be greater than the weight. You feel heavier at the bottom. Now, by extension, that must mean that at the top, the normal force has to be less than the weight. Now, in your notes, for you guys who are just learning this for the first time, it would be a really good idea to write down the unbalanced force must be towards the center. The force must be unbalanced towards the center. That's an excellent thing to be always thinking about. So regardless of the situation, to travel in a circle or in any curve, the force must be unbalanced towards the center. And there's more. When you evaluate these two, evaluate them differently. The one on the bottom, make upwards positive, because that has to be the direction of the acceleration. The acceleration has to be towards the center. So you want to make upwards positive because that's the direction of the acceleration, while at the top, you want to make your evaluation at the top with downwards positive, because the acceleration is now downwards at the top. So don't stay fixed on a coordinate system. Change the coordinate system so that it's always pointing in the direction of the acceleration. All right, so at the bottom, pretty straightforward, right? We know net force has got to be equal to MA. And it's not just any MA now, it's MAC. It's traveling in a circle. Which means the normal force up minus the 600 down has to equal 60 times, we have a choice to make. Do we use V squared over R, or do we use omega squared times R? Which one do you think would make the most sense here? Sure, I think so too. Now you could always use V equals omega times R to find the other one out if you want. That's why we know there's two of these. But we already have this. However, can you use it like it is right now? Can't. You can only use omega if it's in terms of radians and seconds. So you will have to convert it, which is not much to do here since it's already in rotations per second. All we need to do is cancel the rotations, be left in radians, which means 2 pi on the top and 1 on the bottom. So and that's going to be like 0.628 radians per second. Now, I know that there's an entire problem you have to do now, and you guys should do the math on it. No worries? Now, without doing any math, you realize that the normal force is going to be greater than the weight because I have to add this term to the 600 newtons of weight. So you feel heavier at the bottom. That's that oomph when you get to the bottom. The top's not going to be like that. So I don't care what the number is. You can type. We'll do that in a minute. I want to do the top. We have to switch things at the top. Down is now positive. So it's going to be 600 minus n. N at the top, n at the bottom. And that's going to equal MAC. It's a reminder. This is centripetal acceleration. I'm going to keep putting that C there as a reminder that it's a different kind of acceleration. So this will be 60 times omega squared times R. Now you're going to solve this for normal force at the top, and hopefully you see this, that I'll have 600 minus 60 times 0.628 squared times 15. You all right there, Bianca? All right. Now I am interested in this answer. Because there's something interesting in this answer. Or potentially interesting in this answer. What do we get for the normal force on the top? I'm sorry, I can't hear you. 245? Okay. All right. Now, clearly you're lighter at the top than you are at the bottom. You're not actually lighter. You feel lighter, right? Because you're using your weight as part of the force that's necessary to pull you downwards into this curve, right? The unbalanced force has to be downwards, so we're relying on the fact that your weight is downwards to do so. But what's interesting is, go back for just a minute. Before we put all these numbers in, to right here, this step right here. If you really, really want to see something, go back to what was there before. 600 was mg. The 60 is m. This is omega squared times r. Now, I'm putting this all here because if you're the ride operator, if you're the guy with like 3 teeth who takes the tickets and lets you get on there and says, yep, this is safe, it's not like he can change the radius of the ride. That's going to be fixed. And it's not like your mass or gravity are going to change. But do you think he's got a dial there where he can make the ride go faster or slower? You understand that there's a minus sign here. Every time he makes the ride go faster, you're getting closer and closer to the possibility that the normal force is going to get smaller and smaller. You know what happens when the normal force becomes 0, right? It means you're no longer in contact with the chair. That's a limiting function. Now, I'm not saying the right operator knows where that threshold is. I am saying that if you set this equal to 0, you can find out the maximum speed that you can spin a Ferris wheel before you start flinging people off of it. Because that's exactly what happens. You go faster than this, then there's not enough downward force from gravity for you to stay on the ride. Gravity would cause you to be a projectile, and you'd have a parabolic path, not a circular one. And although it sounds funny, did anybody ever ride Gwazi before they shut it off and then rebuilt it? I've not ridden the new Gwazi, but the old Gwazi, besides beating the tar out of you because it was rough, it had several points on the ride where you got very close to a normal force of 0. That was its goal. It was designed to be like this Coney Island wooden roller coaster. It was a replica of it. And wooden roller coasters in general are trying to get you close to a 0 normal force, so you feel like you're being thrown out of the cars. And they heighten that fear by making the track rough and by putting just that little bar in front of you to really ramp up that fear quite a bit. Has anybody had a chance to ride Velocicoaster yet at Universal Studios? Highly encourage it. If you like roller coasters, there are several inverted drops where you go over the top of the track and the normal force goes well below 0, where you need an additional downward force to keep you going in the circular track, meaning you come up against your restraints, and it's the restraints that allow you to travel around the track. They apply an increasing downwards force at the top to provide enough downwards force for the required centripetal acceleration. It's horrifying, but very thrilling. It's a very thrilling ride. It's very well done. Except for the ride, the wait time and the ride show is not great. But this idea we're playing with, very common idea to play with in this class. And we'll talk about a lot, thresholds that involve centripetal motion. So right now we're talking about one, the possibility of spinning a ride fast enough where you get flung off the ride. And there's several versions of this. There's that one, there's the car going over a bump in the road. I give this to you as a homework question where I give you a radius of the road and the car has a tangential velocity. And we ask, what is the max speed that the car can travel at and not leave the road surface? That would be the moment that the normal force goes to zero. That's the maximum. Because there's nothing holding the car onto the road. If you go fast enough, you'll require more downward force than mg can provide. So your car has to open up. It's not going to travel along the road surface. It becomes a projectile. So, again, that's a very common problem that we're going to be discussing. And we're just scratching the surface because there's also there's only one of these that's truly circular at Busch Gardens, and that's the Scorpion. All the other loops at Busch Gardens have adjustable or changed radiuses. I guess you could, what's that? Tigris is pretty circular, but it's different. I don't like Tigris. There's lots of problems with it from just my opinion, but I don't like the corkscrew part at the top where you're, I don't know. Yeah, I don't like it. But what I really don't like is it takes forever to get on the ride, but doesn't hold many people. It doesn't serve many people because it's not a looped track. So they have to stop everything, get everybody off, and then put a new group on. That's why it takes so long to get on there. The other rides like Shikra, Montu, Kumba, they can be running 2, 3, 4 cars at a time. Shikra can handle 5 cars on the track at one time. If they want to, if they have enough people working, they can do that. Which means there's always people on the ride while people are loading. You can't do that with Tigris. Tigris has a single train car, and that's it. Scorpion, they used to have 2 train cars. One loading while one was on there, when it was a popular attraction back in the 80s and 90s, when it opened. But any loop coaster has to have a similar situation. When you make it to the top of the inside of the loop, you guys want to feel as though you're not falling out of your seats. So they try to ensure that you have a fast enough speed sideways so that there's not just weight pushing you into the circle, but also an additional normal force. If they don't do that, then you'll feel like you're coming out of your seat at the top of that loop. But if you ride every roller coaster at Busch Gardens, all of them, you'll feel your seat. You'll feel your butt against the seat when you're inverted. It's on purpose. They don't want the normal force to be 0.